This is example problem 245, chapter 245. We have a wall here that is made up of a steel plate connected to a brick wall, the interface right here. At the outer edge, we have a temperature of 540 degrees Fahrenheit. At the interface here, we are 1.2 degrees Fahrenheit less. We know that on the other side of the brick wall, we cannot exceed 105 degrees Fahrenheit. We know that linearly, we drop in temperature throughout each part of the wall, the steel plate and the brick wall. We know that we are in steady state. We know that the steel plate is a 1/4 inch thick. We do not know, and we want to find the thickness of the brick wall. That's what we're looking for. We're given the thermal conductivity of the steel as 8.7 BTU per hour foot degree Rankine, and we're given the thermal conductivity of the brick as 0.42 BTU per hour foot degree Rankine. All right, so we're looking for the thickness of the brick that will give us this temperature on the outside wall no greater than 105 degrees Fahrenheit. So how do we start here? We know at the interface they have to be the same temperature, and we know that we can go from here to there, linearly dropping, and from here to here, linearly dropping in temperature. All right, so let's set this up. So for the first part, we can say, I'm going to call this equation 1. We can say that Q dot over A, the area for steel, is going to give us minus K of steel times Tm minus Ti all over L of the steel. All right? This is Tm minus Ti over length of the steel. I can say equation 2. Very similar, Q dot over A, this time of the brick. Going to look very similar, KB. This time we're going T outer minus Tm all over length of the brick, what we're looking for. Okay? We don't know this term right here. We do know at the interface they have to be the same. All right? So we know the conduction from here to here, the conduction from here outwards, the conduction into this interface and the conduction out of that interface have to be the same. So we can set these two equal to one another. All right? So the heat transfer in has to equal the heat transfer out. So let's set these two equal to one another. So we can say minus Ks Tm minus Ti over Ls has to equal minus Kb T naught minus Tm over Lb, like so. All right, we can rearrange terms so that we get Lb on this side. This can be Kb over Ks times, I'll move this over here, Ls. On this side, we're going to have T naught over Tm over Tm minus Ti. All right. So far, so good. We can start plugging in our values here. We know this, and this. This one we want to keep less than or equal to 105 degrees Fahrenheit. We'll worry about that in just a second. All right, so let's plug in these terms. All right, Kb 0.42 over 8.7. These are both have the same units, BTU per hour foot degree Rankine. They're going to cancel out, so I'm just going to leave that off for now. Ls 0.25 inch. TO, we don't know yet. We're 105, but we'll wait for just a second. Tm, 540 minus 1.2, 538.8 degrees Fahrenheit over Tm minus Ti minus 1.2 degrees Fahrenheit. So far, so good. LB. All right. If I take this negative, switch it around, I can do that. All right. We want this to be 105 degrees or less, right? This is less than or equal to 105 degrees Fahrenheit, right? That means that LB is going to be greater than or equal to some value if this is equal to 105, all right? So I can say here LB is going to be greater than or equal to 4.36 inches. All right, so minimum, this brick wall has to be 4.36 inches. That will satisfy this outer edge at 105 degrees Fahrenheit. If this is thicker than 4.36 inches, this will be less than 105 degrees Fahrenheit, given that this side of the steel plate is 540 degrees Fahrenheit, as the conduction of heat will go through the steel plate, into the brick wall, through the brick wall, and out the other side.